All right, let's start with part A. So we have the derivative of y is provided us as the quantity squared of 4 minus 2x, 4 minus 2x quantity squared, right? Here we go. So I think at this moment, going back to the procedures for fitting integrants to basic integration rules chart. So this has a lot of different techniques that we can apply. Algebra and trig techniques. I think expand is one of the widely used technique because we have a quantity squared term. So I think that is where we should start for part A. Okay, so I will consider expanding 4 minus 2x quantity squared. So why don't we do that? Here we go. 4 squared is 16 minus twice of 4 and e to the 2x, and that is 8 e to the 2x, and plus e to the 2x, let me just write that clean, e to the 2x quantity squared. Okay, when you have an expression already exponential function raised to the power, so you just multiply the exponents. Okay, so you have 16 minus 8 e to the 2x plus e to the 4x. Okay, so once we simplify this expression, so dy over dx has a better form. So we are given the derivative of a function y. We are trying to find the unknown function y. So we're going to take the antiderivative. We're going to find the antiderivative of this expression here. So in fact, we're solving a differential equation is implicitly related to solving an integration problem. Okay. All right, so far so good. So each term here is different from each other, even though these two look like e to the 2x and e to the 4x look similar. In fact, they are not because they come at different exponents. So all I'm going to do here is split this integral into 3 integrals by divide and conquer technique. So this is 16 dx minus 8 e to the 2x plus e to the 4x dx. Okay, so 16 dx is sort of like an easy shot to go, and you can always, by the way, use the basic integration rules that I provided you earlier in earlier videos. You can find the copies of those in the lecture notes as well. Okay, so eventually, by the way, we're going to use number 6 because we have mostly exponential terms. Okay, so e to the u du is integrated as e to the u plus c. Okay, so going back to here, as I said, 16 dx is not a big deal because the integral of that is just 16x. But here I should use a u substitution. U equals 2x and du equals 2dx for this integral. And I'm going to use a different color for this u substitution here. This time I'm going to call u to be 4x so that du is going to be 4dx. Okay, there's not just one u for all, but once you split the integrals into 2 parts, so you have different you have different u's to work with. Okay, so in one case du equals 2dx, and in the other case du equals 4dx. Let me just continue right from here. All right. So I have 16. Let me just copy that down here. So 16 dx, 16 dx. Okay. Now I have du equals 2dx. So 1 dx is 1/2 du. So in other words, this would be like negative 4 e to the u du. Okay. It's coming all the way to me. It's just approaching to me. All right, so then the other one is like 1/4 e to the u du. But be careful because u's are different here. So for that reason, let me just go with yellow here, and let me go with blue here. Okay, how about that? Okay, so now you know exactly what I'm talking about. All right, so let's finish the integration here. 16x for e to the u, but u equals 2x for the first one, and plus 1/4 e to the 4x, and we have a generic integration constant plus c. Okay, so this should be the final output as the result of this integration, which corresponds to solving the differential equation dy over dx equals 4 minus e to the 2x quantity squared. So y, the solution, is given in the red box. So that means if you take the derivative of that, you should get back to this quantity squared form. Okay? All right. So I'm going to continue part B in the next video. So I'll see you in that video. Bye.